Good morning, everyone. My name is Jun Yang. My advisor is Dorian Abbot. This work is collaborated with Gangwala and Daniel. The title of my talk is Habitable Planets in Venus Orbit and with Modern Venus Slow Rotation. When I say habitable planets, I mean the planets in the habitable zone. Habitable zone means that a planet in these regions liquid water can maintain on the planet's surface. In general, the inner edge of the habitable zone is defined based on runaway or moist greenhouse effect. The outer edge of the habitable zone is defined based on maximum CO2 greenhouse effect. Today, I focus on the inner edge, runaway greenhouse effect. It means that as the surface flux increase, more and more water vapor enter into the atmosphere because water vapor is a very strong greenhouse effect gas. It reduces the outgoing non-wave radiation. When outgoing non-wave radiation is not able to balance the observed shortwave energy, the planet enter into runaway greenhouse state. It means that all of the ocean will evaporate to the atmosphere and escape to space. This figure shows the habitable zone based on 1D radial transport model. Based on this model, Earth is in the habitable zone and Venus is close to the inner edge of the habitable zone. We know that Venus has the similar radius and the gravity of Earth, but their climate is quite different. The surface temperature of Venus is about 300 Kelvin, but our Earth is habitable. The solar flux of Venus is about twice of our Earth. Another quite different perspective is that Venus, the rotation rate of Venus is much slower than Earth. Our Earth have a rotation period of 1 day, but Venus has a rotation period of 243 days. This minus between the number is because the rotation rate of Venus is opposite to our Earth. It means that if you live on Venus, you will see sunrise in the west and sunset in the east. There's two big questions about Venus and the Earth. The big question is, if Venus had oceans during the formation of the solar system, when did it lose the ocean? We know that Venus now have no oceans, but some detections show that Venus may have ocean since its formation. The second question is for our Earth. Will Earth lose its oceans as the sun become brighter with time? Let's start with a short experiment with a 3D global climate model. The experiment is that if Earth is moved to the Venus orbit, what will happen? We use the 3D global climate model and found that if Earth is moved to the orbit of Venus, it will enter into runaway greenhouse state. But if you slow down the rotation rate to the rotation rate of Venus, you will find that it's habitable. It's shown in the black line. The global mean temperature is close to our Earth. But if you slow down the rotation rate, but it doesn't include cloud in the model, it will also enter into runaway greenhouse state. Let's show the temperature, the seasonal cycle of the climate. This is a movie. How do I? Yeah. This movie shows the surface temperature and convective cloud as a function of time. The upper panel shows the surface temperature. As you can find that the surface temperature is in the range of 216 Kelvin and 300 Kelvin. It means that it is habitable. The black dot is the substrate point. It moves slowly around the planet. The lower panel shows the the clouds. You can see that another cloud formed around the substellar point. This cloud strongly increased the planet albedo to about twice of our Earth. Can you yeah. Global mean planet albedo is 0.64. It's about 2 times of Earth. Although the stellar flux of Venus is about 2 times of Earth, but the planet albedo is 2 times of Earth. So the that observed short wave is close to Earth. So you see that the global mean temperature is close to Earth. Why there are not clouds formed around the substellar regions? This figure summarizes the mechanism. On the slow rotating case, the surface of the day side is warmer than the night side. So there's strong convergence from the night side to the day side. Around the substellar point, the strong convergence and convection produce oblique sink clouds. These clouds greatly increase the planet albedo and reflect back the solar rotation to space. So you will see that the surface temperature is close to our Earth. On the slowly rotating planets, the circulation is like a global skywalk circulation. It's upwelling on the day side and downwelling on the night side. I will talk more about details of this maxim and how we do the simulation in the next slides. We use 3D global climate models, CAM3, CAM4, and System 3. All of the models are developed by NCA. The model uses array of fan-walled dynamic core, and it includes deep convection, shallow convection, and large-scale condensation and clouds. The model is coupled to a slab ocean or dynamic ocean. A slab ocean means that the ocean has no motion. But for dynamic ocean, the ocean is driven by surface winds and salinity difference between different regions. We have tested the radiative scheme, and we found that the radiative scheme is actual as long as the surface temperature is less than 314 Kelvin. Our simulation is well in these regions. We do some modification of the model, include change the rotation rate, the orbital period, and obliquity and eccentricity. We do a series of rotation period from 0.5 days to 314.5 days. The atmosphere composition is 1 bar nitrogen plus water vapor. I should mention that when we change the rotation rate, we not only change the correlative force, we also change the length of the day and night. The length of 1 day on Venus is about 200 days. It means that if you live on Venus, you need to walk continuously for 200 days and sleep another 200 days. This figure shows the surface temperature and the planet albedo as a function of rotation period. The left panel shows that as you increase the rotation period, the surface temperature decreases. But if you turn off the clouds in the model, you find that the surface temperature is nearly independent on the rotation period. As long as the planet under very slow rotating rate, the radiative fan effect also acts to cool the planet. So this figure shows that slow rotating planets is much cooler than rapid rotating planets. And the main factor is that the slow rotating planets has much higher planet albedo than rapid rotating planets. The planet albedo is mostly contributed from the clouds. On slow rotating planets, the strong convergence and convection on the day side produce very oblique sync clouds at the substellar regions, which reflect back the solar radiation to the space. On rapid rotating planets, such as our Earth, there's only a narrow region of the deep chalky because there's oblique sync clouds. These clouds have a really small effect, small contribution to the planet albedo. So this figure explains why the slow rotating planets is much colder than the rapid rotating planets. For the slow rotating planets, the whole planet acts like the tropical of our Earth, a strong convection and strong convergence on the day side. Next, I want to answer a question is that how does clouds influence the inner edge of the habitable zone? This figure shows the x-axis the stellar flux, the tensor stellar flux to our Earth. The y-axis is the star temperature. I plot some plans of our solar system, Venus, Earth, and Mars, and some exoplanets. Based on 1D radiation transfer model, the green line shows the inner edge, the blue line shows the outer edge. This model doesn't include clouds. If we include clouds, use 3D model, we found that the inner edge moves close to the star. This is because include clouds and the unsaturation of the atmosphere. If we further investigate the slow rotating planets, we found that the inner edge further moves close to the star. This means that a lot of exoplanets which was thought too hot may be habitable if it rotates slowly or be tightly locked. So, questions and comments. Thank you for your attention.
Hi, I noticed in your plots when you first start out the global mean surface temperature is around 287 K, and if I understand, this is the same world that you published in earlier this year. So I wonder how you get your planet at 287 K when it has no obliquity and you get a lot of ice at the poles. It seems strange you get the same surface temperature of the Earth. So I'm wondering if there's some other things that you tuned in your model to get the surface temperature to be Earth's, when this is definitely not Earth. Because you also, in that model, changed the land albedo, if I remember correctly, and a few other things.
We didn't tune the model. We just changed the Earth model to the Venus orbit. And we include sea ice. We also include dynamic ocean. We do different sensitivity tests with continents or no continents at all. We found that the results is quite similar because the cloud dominates the planet albedo.
Yeah, hi. So I noticed that your atmosphere doesn't have oxygen. Can you add more details to that?
Yeah, we didn't include oxygen, but oxygen may have a strong effect on the stratosphere, but a very small effect on the surface temperature.
I was looking at your cloudiness slide, and it looked like all your clouds were over land, not over oceans.
Yeah.
In the Earth simulation, is that true?
No, this is the low panel is the cloud, convective cloud fraction. You can see that the clouds forms around the substellar regions, both over the land and over the ocean.
Okay, thank
Hi. So you showed us some plots of global albedo and how that changes, but I think the more interesting thing is it's not so much that the global albedo changes, but that the albedo on the side of the planet that the sun is shining is much higher. It would be interesting to see a plot of global absorbed solar radiation as a function of rotation rate, so that you could see how the global energy balance depends on rotation rate.
Because the night side has no solar radiation, so when I say global mean planet albedo, only the day side has contribution to the albedo, because on the night side there's no solar radiation. So you are good. Your suggestion is very good. I need to plot it.
Okay, so you did only consider the albedo on the sunlit side of the planet? As
on the day side.
Okay.
Yeah.